Hi everybody, welcome to the first lesson in chemistry. We're in Unit 1A. We're going to be talking about atomic structure and nuclear chemistry in this unit. In today's lesson, we're going to be focusing on the basics of the structure of atoms, what atoms are, and also a little bit about something called isotopes. All right, so first things first, to kind of get us into the mood here, we got a little cartoon. Hey, Mrs. Olson, why did you mark me wrong? Question number 4. She says, draw the parts of an atom. You left it blank, Caulfield. He said, I drew it to actual size. So the point here is that obviously atoms are tiny, tiny, chuckle, chuckle. All right, so what really is an atom then? Well, an atom is basically the fundamental unit of an element. You can think about atoms as being the smallest pieces of an element that would still retain the identity of the element. So, if I've got a gold atom, then the smallest piece of gold that I could have that would still technically be gold would be a gold atom. Now, there are parts of atoms, and if you start, breaking this down even further, then you might not have gold anymore. But the smallest fundamental unit of an element is an atom. All right, now, elements can exist as pure substances or as parts of compounds, and most of the time they exist as compounds. You could have something like, pure gold, which would just have a chemical formula of AU. You could have pure hydrogen, which would have a chemical formula of H2. It tends to be a diatomic element. You could have pure oxygen. Oxygen is another one of those elements that tends to bond to itself, so its chemical formula would be O2. But if you had some water, the chemical formula is H2O, showing that hydrogen and oxygen have bonded together in a ratio of 2 hydrogens to 1 oxygen. So this right here is an example of a compound. So we don't have the element all by itself anymore in something like water. So anytime you see a chemical formula that has more than one element in it, we're talking about a compound and not just an element. Okay, now, something you need to know about elements and the way that we express them on the periodic table. If you look at the periodic table, you're going to see a bunch of chemical symbols on the table. Now, chemical symbols are basically just one or 2-letter ways of writing a shorthand for elements. So example, if you look at an element like potassium, which would be about right here on the periodic table. Potassium has a chemical symbol of K. And so watch out, the 1 or 2 letter symbol for many elements is not the same as the first 1 or 2 letters in the name. It is for some, but not for all, obviously. We've got hundreds of elements and only 26 letters in the alphabet. So a lot of the symbols come from old Latin terminology and things like that. You can see that a lot. Something like lead, has a chemical symbol of PB. This PB symbol came from plubus, which is Roman for pipes, or Roman for plumbing, and because they used lead for plumbing. Of course, that was a bad idea because people started getting lead poisoning and they had no idea while they were going blind and crazy. But anyway, all right. So if you get into human history and how our understanding of atoms has evolved throughout the years, you can really go all the way back to 460 BC. We're talking about the philosopher Democritus. Now, philosophers weren't people that actually did any experiments, but this guy Democritus, was just theorizing one day and said that what if you took a loaf of bread and you cut the loaf of bread in half, and you cut the halves in half, and you cut the quarters in half, and you kept cutting it into smaller and smaller and smaller pieces. He was thinking that eventually you would get down to some little tiny piece that was indivisible, that could not be split anymore. And so that's actually what the word atom comes from. The word atom comes from the Greek word atomos, which means indivisible. Now, when we finally got into some science in the 1800s, Dalton published a theory that basically said that atoms are these hard, indivisible spheres that Democritus was saying that they were, and we now know that there's some parts to atoms. So that much of it was found out later to be not true. But the really important thing that Dalton said was that pretty much every atom of the same element is identical to every other atom, which is close to being true. And he also said that every atom of each element is unique from atoms of other elements. So that was something that really held on for later years. Now, once we got into the electrical age, this guy named Thomson started playing around with electricity flowing across a cathode ray tube. And basically, he was just watching an electricity arc inside a glass tube, and found out that he could take some magnets and bend this arc of electricity, and the electricity was coming out of wires. And he said, okay, the atoms in the wires have to have some charges if they're able to be attracted or bent by a magnet. So he was the first guy to come up with a model of the atom that had charges in it. We called this the plum pudding model of the atom. He was a British guy, so he's saying that it's kind of like the atom is some pudding, and the negative charges in there are the pieces of plum inside the positive pudding. And then a little later on down the road, not too long, within a decade, this guy named Rutherford, who worked closely with Thomson, came up with the idea that atoms had a middle where all of the weight of the atom is, called a nucleus. And we'll talk about the experiment that he did in just a second. But the model of the atom went to a nuclear model in 1911. And then a couple years later, this guy named Bohr, who was heating up elements, noticed that different elements gave off different colors, and he was trying to explain that, and came up with a theory that atoms' electrons resided in these energy levels. And so we kind of published theories that had a nucleus, and a theory that the electrons, these are the negatively charged electrons, and this is positive here in the middle, in Bohr's model of the atom. These electrons resided in these orbits that were in certain distances from the nucleus. And then our final model of the atom, and this is still the most current model of the atom, even though this model was published in 1926, is the electron cloud model of the atom, or sometimes we call this model the wave mechanical model of the atom. It's our most current model of the atom. Now, this one's a little bit more complicated. We're not going to get into talking too much about the wave mechanical model of the atom until we get into Unit 1B. So in Unit 1A, we're going to be focusing mostly on the Thomson and the Rutherford, the Rutherford and the Bohr models of the atom in this unit of study. Okay, so let's go ahead and start going inside the atom and start looking at the parts of the atom. So what are atoms made of? Let me go back to Rutherford just for a brief moment. If we talk about, how did Rutherford discover that the atoms had a middle, that the atoms had this thing called the nucleus? Well, he was experimenting with some radiation, and so he basically put some radioactive material in a black box, poked a hole in the box so that the radiation could only get out one way. And he wanted to see how well the radiation, or how it bounced off of materials and how it was deflected and refracted and all that kind of stuff. So he started shooting this radiation at this little tiny thin sheet of gold foil. And it was only, maybe a few 100,000 atoms thick. So pretty thin sheet of gold foil, although gold is a heavy atom. And what he noticed was that most of the radiation went straight through the foil. It didn't bounce off. A little bit of it bounced back, but most of it went through the foil. And so he was trying to think of, well, wait a minute, this is a solid sheet of gold foil. How is this radiation going through the foil without making any holes in the gold foil or anything like that? And the idea is he came up with this model of the atom. He said, okay, if this gold foil is made up of these atoms that have most of the weight of the atom in the middle of the atom, these are atoms with this center where all of the weight of the atom is, and there's some empty space between the center and the edge of the atom, then if you were to, shoot the radiation at this atom and it hits right there, assuming it's going like straight into the board here, then it wouldn't hit anything and it would go straight through. But if, you hit the nucleus when that radiation was going through, then the radiation might actually bounce back. So this was just a model of the atom that said, hey, atoms are mostly empty space because, it goes through most of the time. And it only bounces back when it actually hits the center of the atom where all of the weight of the atom is. Okay, so atoms are made of three things. We call these things subatomic particles. The three subatomic particles that are most important are electrons, protons, and neutrons. Now, for our purposes, we're going to kind of simplify the mass a little bit. The mass of protons and neutrons does differ slightly, but for all practical purposes, protons have a mass of 1. Okay? Now, 1 what? Well, the mass of subatomic particles is typically measured in an atomic mass unit, or AMU. And this is a tiny, tiny little unit of measurements, ever so much smaller than a gram or milligram or nanogram. AMUs are very tiny units used to measure individual subatomic particles and individual atoms. The technical definition of an AMU is it's 1/12 of a carbon-12 atom, but that's not really important right now. All right, now neutrons also have a mass of 1 atomic mass unit. Electrons, on the other hand, have a mass that is so tiny, it's like 1/2000th of a single atomic mass unit, that for all practical purposes, at least for the purposes of this course, we're going to say that electrons essentially have a mass that's 0. Now, that's not actually true. Something on the order of 10 to the negative 31st kilograms, which is ridiculously tiny, but it's basically just so small that it doesn't matter. We're going to say that the mass of electrons is negligible. All right, now when we go to look at the electrical charge of subatomic particles, protons have a charge of +1, electrons have a charge of -1, and neutrons have a charge of 0. Okay? Neutrons have no charge. Now, if you look at an actual picture of the atom, here's a kind of a Rutherford model of the atom, it's going to show the protons and the neutrons together inside the nucleus of the atom. So the protons and the neutrons both reside in the nucleus. They both make up the nucleus of the atom, the middle of the atom. Whereas the electrons are outside the nucleus, and Bohr's model had these guys orbiting the nucleus, but basically we're outside the nucleus with the electrons. Okay? This area outside the nucleus in the most recent model of the atom, the wave mechanical model of the atom, is known as the electron cloud. Even one electron apparently can make a cloud in the electron cloud, but there you go. Okay, so really important to understand, electrons are negative, protons are positive, neutrons are neutral, and out of the three particles, electrons are the ones that have no mass, or no significant mass anyway. All right, now if you go to a periodic table and pull a box out of the periodic table to examine an element, there's a lot of information in this that can basically tell you what the structure of the atom is, okay? Every periodic table for every element is going to show a whole number. This is the smaller number that's in the box. Now, different periodic tables can have these numbers in different places, but the small whole number in the box is known as the atomic number. And it's really important to understand that the atomic number is always going to be equal to the number of protons. Okay, basically, we're saying that those are the same thing. Okay, so the atomic number and the protons are the same thing. Now, the atomic mass, we'll get into this a little bit more later. This number is actually an average of different carbon atoms that have different weights. We'll talk about isotopes here in just a little bit. But basically, all carbon atoms don't necessarily weigh the same. And so this number doesn't represent one carbon atom. This number is an average of carbon atoms that can have different weights. It's a weighted average. You'll always see a symbol in the box for the element to let you know what element it is. Our periodic table may not have an element name, so it's really important that you start learning element names so that you can use the periodic table reference sheet that's going to be provided for this class. You need to know which names go with which symbols for most of the elements. And then finally, and this is not a piece of information that's on the box, okay, so kind of deviate for a second. But a mass number, now this is a little bit confusing because it's not the same thing as an atomic mass. A mass number is the sum of the protons and the neutrons, okay? So if you put all the protons and the neutrons together, basically how much the nucleus of the atom weighs, that's the mass number. And if you want to think, why the electrons didn't get it added in there, well, remember the electrons were the ones that didn't really weigh anything. Okay, now a lot of times the mass number of a particular atom will be close to the atomic mass, but not always. And so that's an important distinction. The mass number and the atomic mass are not exactly the same thing. We're going to be focusing more on the mass number and less on the atomic mass, at least for right now. Okay? All right, so what element is pictured below? Well, if you take a look at this picture, you can see we got some protons and neutrons and electrons in here. But out of everything that's there, which thing is the most important to look at? Well, remember, the identity of an element is based on its atomic number. So the number of protons really is the only thing that you have to look at here. This has 3 protons. And so if you go to the periodic table, you can look and see, hey, which element on the periodic table has 3 protons, and it's going to be lithium, okay? Now, I know it's lithium because this picture of the atom has 3 protons. I'm going to abbreviate protons with a little p, maybe with a positive on it. So it's got 3 protons. I know it's lithium. What's the mass number of this atom? Well, remember, mass number was equal to the number of protons and the number of neutrons added together. So if I am seeing this picture correctly, this looks like we've got 3 protons, and it looks like we've got 4 neutrons in this picture. So it looks like the mass number of this atom would be 7. Okay? Now, what did we not include in the mass number? Well, we didn't include the electrons. Why didn't we include the electrons? Well, the electrons have essentially no mass. If I say they have no mass, that's not exactly true, but they have so little mass it doesn't matter. So the mass is essentially 0 for electrons. Okay? All right, so to recap, we know it's lithium because it's got 3 protons. The mass number's got to be 7 because the mass number is the protons and the neutrons added together. And the electrons are not in the mass number because they don't weigh anything. Okay? All right, so to kind of reiterate what we just said, an atom's identity is always determined by its atomic number, okay? So the identity and the atomic number are forever linked, okay? Now remember, an atomic number is always equal to protons, always equal to protons. That's the definition of an atomic number. The atomic number doesn't have to be the same as the other subatomic particles, just the protons, okay? Now, the atomic number, though, can also be the same as the electrons, but this is only going to be true if the atom is neutral. Okay, now, when we say that an atom is neutral, what we mean here is that the total charge inside the atom equals 0, okay? And the idea here is that, since protons are positive and electrons are negative, if you take the number of protons and the number of electrons and you have an equal amount, then the positive and negative charges is essentially canceling out with each other. So, imagine I had that atom of lithium in the previous picture. If I've got 3 protons and 3 electrons, this atom is neutral because if you look at these two, positive 3 and negative 3 from my 3 protons and my 3 electrons is going to add up to a total charge of 0. So it's neutral because the total charge is 0. That's going to happen anytime the number of protons and the electrons are the same. Okay? Now, your mass number, again, that was the protons and the neutrons added together. We didn't include the electrons because the electrons didn't weigh anything. Okay? All right, so let's see if we can just predict how to get the protons, neutrons, and electrons off of a box in the periodic table for a couple of different elements. So for this first example, how many protons, neutrons, and electrons would be in an atom of fluorine? Well, if you look in the box, you can see that the atomic number of fluorine is 9. Okay, so that tells us the number of protons. So we know we're going to have 9 protons in an atom of fluorine. Now for the number of neutrons, remember, that's not given to you in the box directly, but the mass number is equal to the protons and the neutrons added together. Well, if you look at fluorine, this atomic number is probably pretty close to the mass number. If we round this number off, this number is about 19. Okay, so let's assume for a second that the mass number of this atom of fluorine is 19. Well, if we knew that was 19, and we know that's 9, then what does the number of neutrons have to be? You could just subtract. 19 minus 9 would give you 10 neutrons. So we know that this atom of fluorine probably has 10, I'm sorry, not electrons, 10 neutrons. Now we're going to assume this atom is neutral. So if we wanted to know how many electrons there are, remember the atomic number can also equal electrons if the atom is neutral. So we're going to say that the electrons are just the same as the number of protons in this neutral atom of fluorine. Okay? All right, one more example, a little faster this time. How many protons, neutrons, and electrons would be in an atom of sulfur? Okay, well the atomic number for sulfur is 16, so we know there's 16 protons. To get the neutrons, we would need to subtract the mass number minus the protons to get the number of neutrons. Well, on sulfur, the mass number is 32. So, for this one, we could do 32 minus 16 and get 16 neutrons. This just happens to be the same as the number of protons here. It doesn't always have to be that way. You can see that in the last example. Okay, but we got this by doing 32 minus 16, mass number minus atomic number. Okay, and finally, the number of electrons, if this atom were neutral, would be 16. So here's a case where all 3 subatomic particles, the protons and the neutrons and the electrons, all ended up happening to be 16. Okay? All right. So now, let's get into this idea of isotopes. So isotopes are different versions of the same element. But we need to start off with a premise here that basically says that atoms of the same element always have the same number of, which subatomic particle has to be the same? It's the protons that always have to be the same. Okay? Now isotopes are atoms of the same element, which by the way means that their atomic number and the number of protons is the same, that have different mass numbers. And the reason they have different mass numbers, if the protons are the same, this is the thing that's going to be different. It's the neutrons. So they've got different mass numbers because they have different numbers of neutrons. Taking a look at a simple example here. Okay, Here's an atom of hydrogen. It's got one proton, and it's got one, this is an electron here on the outside of the atom, okay? Now this picture says deuterium, but really this is hydrogen as well. Deuterium is just a special name for this particular isotope of hydrogen that weighs 2, but it's just got an extra neutron. But it's still the same element, it's still hydrogen because it's only got one proton. Here we've got tritium. Again, this is still just hydrogen, so I don't want to mislead you there, because it's got, again, only one proton. So that still makes it atomic number 1, which is still hydrogen. This hydrogen atom just happens to weigh a little bit more. Okay? So isotopes are atoms of the same element that have different mass numbers because they have different numbers of neutrons. The neutrons is the thing that's different here with these different versions of hydrogen, these different isotopes of hydrogen. Now, notation is just a way to write something. So if you want to write an isotope without necessarily drawing a picture of it, there's a shorthand way of doing that. You use the element symbol, and you use numbers on the top left and bottom left. And this is, you know, you want to make sure it's on the left of the symbol, not the top, like where an exponent or something like that would be. So this is a little bit odd for people who are used to, you know, exponents in math and things like that. But basically, you're going to write a superscript and a subscript. The top number, the superscript, is going to be the mass number of that atom, and the bottom number is going to be the atomic number. Okay, so it shows two different versions of carbon. Carbon with a mass number of 12 and carbon with a mass number of 14. This one represents this atom that has 6 protons and 6 neutrons. This one represents this atom that has 6 protons and 8 neutrons, and the 6 and the 8 add together to give you that isotope mass number of 14 on the top there. Now, if you look at the periodic table, at a box for carbon, carbon's atomic number of 6, and down at the bottom its mass is like 12.01, okay? So this is an average of these different versions of carbon. The reason the average is pretty much 12 is because out of these 3 different versions of carbon, carbon 12 is the most common. You know, more than 99% of carbon is carbon 12, and less than 1% is carbon 13 and carbon 14. So when you average these together, there's a whole lot more of these in the average, and so that makes the average much, much, much closer to 12. Carbon 13 and carbon 14 are more rare. Okay? Now, another way that you can write a isotope notation is with basically just the element's name and a dash. So if you see carbon 12, carbon-12, that's telling you, hey, this is carbon with a mass of 12. Okay, because you can look on the periodic table and you can see carbon has an atomic number of 6, and that's never going to be different for carbon, but the mass number can be different. So if you're going to talk about different versions of carbon, really the most important piece of information about those different versions of carbon is going to be the mass number. So if you just write the element name and a dash, and that number after it would be the mass number. Okay. All right, so let's recap this isotope notation idea just for a second. Got a couple of examples here. It says how many protons, neutrons, and electrons are in each of the following. Okay, so here we've got this isotope of aluminum, and we got a number 27 on the top and a number 13 on the bottom. Okay, now remember, the top number is the mass number, and the bottom number is the atomic number. Well, the atomic number tells us how many protons we have. So that bottom number tells us that we're going to have 13 protons in this atom of aluminum. The number of neutrons, on the other hand, this is the one you're going to have to subtract for, because the number of neutrons is not given here directly, but since the mass number is equal to the protons and the neutrons added together, if you know the mass number and you know the protons and you want to find the neutrons, then basically all you would have to do is just do neutrons equals...
Teachers, we have some students in ROTC that are willing to help if you need any sort of help with packing or carrying things.
So the neutrons equal the mass number minus the protons if you needed to subtract. So in this example, if we did 27 minus 13, that would give us 14 neutrons. Okay? And then the bottom number is the atomic number. Now, if we assume this atom is neutral, then the protons and the electrons would be the same. So we could say this has 13 electrons as well. So 13 protons, 14 neutrons, 13 electrons. Okay? Now, for this atom of sulfur here, the bottom number is 16, so we would know that we've got 16 protons. If we subtracted, we could get the number of neutrons. So 32 minus 16 would be, again, 16 neutrons. That was a coincidence. And then also 16 electrons. So sometimes they can all be the same. All right, let's try a couple going the other way. What if we know the protons, neutrons, and electrons, and we need to get ourselves to an isotope notation, so something that looks like this? All right, well, remember, the bottom number is the atomic number. And the atomic number also is the same as the number of protons. And so in this example, if I've got 5 protons, I know that bottom number is going to be 5. That number 5 also tells me what element it's going to be. If you look at the periodic table, element number 5 is boron, which has a symbol of B. The top number is going to be the mass number. And remember, the mass number is equal to the protons and the neutrons added together. So the 5 and the 6 is going to make that mass number be an 11 there on the top. Okay? So what's going to be different in this second example? Well, really the only thing that's going to be different is just your mass number, because we changed the neutrons here. And the bottom number would be 5, the top number would be 10, but it's still boron because we still have 5 protons, okay? So this is an example of 2 different isotopes of boron. Okay, let's see if we can use some other skills here. All right, so this is just a little chart. It's got some information about an atom given to you, and some information is missing for that atom. Okay. All right. In the first row here, we've got hydrogen. It's got an atomic number of 1 and a mass number of 1, and it wants to know how many protons it's got, how many electrons, how many neutrons, and then this isotope notation, which is what we were doing on the previous slide there. So the number of protons has to be the same as the atomic number. So this would have to be 1. If it's a neutral atom of hydrogen, the protons and the electrons have to be the same. So the number of electrons would also be 1. Now, to get the neutrons, this is where we subtract, right? The mass number minus the atomic number, or the mass number minus protons, is going to give you the number of neutrons. I've heard people teach this way, and if you line it up like that, you know, mass number minus atomic number makes neutrons. We call this the Mann equation. But that's an easy way to remember how to get your neutrons. Just mass number minus atomic number gives you neutrons. Well, in this case, mass number minus the atomic number, or mass number minus protons, 1 minus 1 means this atom doesn't have any neutrons in it. Okay? For the isotope notation, remember, this is where you've got the symbol and a number on the top and the number on the bottom, and that top number is the mass number, and the bottom number is the atomic number. So if we were going to do that isotope notation for hydrogen here, then the symbol would be H for hydrogen. The top number is the mass number, which would be a 1, and the bottom number is the atomic number, which is also 1. So this is H with a 1 on top and a 1 on the bottom. For the next example here, it didn't tell us what element it is. So how could you figure out what element it is? Well, remember, the element's identity is determined by the atomic number or the number of protons. And it doesn't give us protons, but it does give us the atomic number. So we know that this has to be element number 8 on the periodic table, which is oxygen. Well, the atomic number also tells you the number of protons would be 8. And if it's neutral, the number of electrons would also be 8. Now, if you look on the periodic table, the weighted average atomic mass of oxygen is 16, and so this is not your most likely version of oxygen. This is oxygen with a mass number of 17. But if we know this piece of information, we've got to use it to determine the number of neutrons. And say the number of neutrons would be the mass number minus the atomic number. So if we did 17 minus 8, let's see here, we'd get 9 neutrons in this case. For the isotope notation, we're just putting in information we already know. We already know that the atom is oxygen for the symbol. We already know the bottom number is 8 for the atomic number. And we already know the top number is a mass number of 17 for this atom. Okay? All right. Next one, we got sulfur. Now, if you look on the periodic table, sulfur is atomic number 16. Now, a mass number is technically equal to the protons and the neutrons added together. Now, right now, we don't know what the protons are. So, but we have an atomic number is 16 since it was sulfur, so we know the protons are 16. And mass numbers, protons and neutrons, we don't know what the neutrons are. Okay, so if you don't know the mass number or the neutrons, you're probably going to have to go to the last resort of rounding off the number on the periodic table. So if you look on the periodic table in the box for sulfur, you'll see that, 32.0 whatever. So the mass number we're just going to assume is 32 in this case. To get your neutrons, you could subtract mass number minus atomic number to get neutrons. So 32 minus 16 would be 16. The isotope notation will be sulfur with a mass number on top of 32 and an atomic number on the bottom of 16. Okay. All right, for the next one, we got different information given. We got the protons and the neutrons this time. All right, so we don't even know what element this is, but which thing can tell you what element it is? It's the number of protons. Remember, protons tells you the atomic number, tells you the element's identity. So we know if this thing's got 9 protons, then it has to be an atom of fluorine, element number 9. Now the mass number, by definition, is the protons and neutrons added together, and we actually know both of those pieces of information this time. So we're going to say the mass number is 9 protons plus 10 neutrons is 19. The number of electrons, if this is a neutral atom, would be the same as the number of protons, so that's 9. And the isotope notation would be fluorine with a mass number of 19 and an atomic number of 9. Just use the information you've already got there. Okay? For the very last one, a little faster this time, number 19 is, or 19 protons tells us the atomic number is 19. And if you look for element number 19, you're going to find K, potassium. The protons and the electrons are the same in a neutral atom, so 19 and 19. The number of neutrons you could subtract for. So if we've got a mass number of 41 and we subtract 19, let's see here, we're going to get, what is that, 22 neutrons this time. And if we use the isotope notation, then our symbol is K. Our bottom number for the mass, or the atomic number is 19, and the top number is the mass number that we already knew was 41. Okay? All right, so just a little practice there to try to help you understand the relationship between these different particles and how you can use your periodic table to get a lot of this information. Okay? All right. That will end the lesson this time.